The larynx is used in speech to create the distinction between phonation and non-phonation. Phonation provides a sound source for vowels and for resonant consonants, so sounds like E, L, or N. Phonation is also part of the distinction between voiced and voiceless obstruents, like the difference between T and D, and the difference between S and Z. Phonation is also altered as part of the intonation of a sentence, so the frequency of phonation is altered, changing pitch, and also the intensity is altered, changing loudness. There are smaller differences in types of phonation that give us different voice qualities or registers, like a breathy voice quality or a creaky voice quality. And finally, the larynx is also used to create a sound source in whispering. Our theory of phonation is the myoelastic aerodynamic theory. In this theory, air pressure is what opens the vocal folds, and elasticity of vocal fold tissue is what closes the vocal folds. There's a cycle of vibration that occurs if the balance between air pressure and elastic tension is just right. So phonation is a vibratory process that depends upon the interaction between subglottal air pressure and the elasticity of the vocal folds. When we phonate, the vocal folds open and close in cycles, releasing puffs of air at a rate called the fundamental frequency, or F0, in units of cycles per second, also known as hertz. Phonation is also referred to as voicing in some discussion of distinctions between speech sounds. Phonation occurs during the glottal cycle. The glottal cycle starts with respiratory expiration, airflow out from the lungs. You then adduct, the vocal folds to bring them together. This closes off the glottis. Once the glottis is closed, subglottal pressure increases. Eventually, that subglottal pressure increases beyond the tolerance of the elastic forces, and the glottis is pushed open, the vocal folds are pushed apart. Once that subglottal pressure is released, the pressure decreases, and the elastic forces once again overcome that pressure, and the glottis closes. After the glottis closes, subglottal pressure increases, and the cycle continues. This cycle continues until the vocal folds are abducted, opened, to stop phonation. Looking at the glottal cycle in more detail, we first start with expiration. So accessory muscles of respiration are used to maintain a constant positive subglottal pressure for speech. Remember that expiration during speech occurs during 90% of the respiratory cycle. Our phonation and all of our speech is ceased during inspiration. It only occurs during expiration. Inspiration is usually timed to occur at appropriate junctures in the utterance, between sentences, or between major phrases or clauses. Adduction of the vocal folds is done by interarytenoid muscles, both transverse and oblique, bringing the arytenoid cartilages together, and the lateral cricoarytenoid muscle, rotating the arytenoid cartilages to bring the vocal processes of the two arytenoid cartilages together. These actions will close off the glottis, though there's some variation in these actions on the basis of voice quality. Once the vocal folds are closed, subglottal pressure increases. So with the vocal folds adducted, the glottis closed off, the body of air below the glottis is fixed, but expiration continues and the lungs continue to be compressed, so that increases pressure below the glottis. Eventually, that pressure builds to a point where adduction of the vocal folds is not strong enough to keep the glottis closed. The air pressure pushes the vocal folds open. That air pressure is released. However, the muscles continue to hold the vocal folds in an adducted position. They are just pushed apart by air pressure. So there's no muscular activity to abduct the vocal folds until all phonation is stopped. Adduction, adduction, occurs throughout the glottal cycle. Once the vocal folds are opened and the subglottal pressure is decreased, air escapes, and this reduces the amount of air in the lungs and reduces the air pressure. In addition, air that's moving between the vocal folds acts on them with a lower pressure than air that is not moving. This is a fact of physics known as the Bernoulli effect. The Bernoulli effect is a finding that the more rapidly a gas or a fluid flows through a tube, the less the air pressure is against the side of the tube. The rate of flow of air gets increased at a point of constriction, such as the vocal folds in the vocal tract. So when air is flowing past the vocal folds, it goes past rather quickly because of the constriction, and this results in abnormally low air pressure between the vocal folds compared to elsewhere. In the case of something flexible, like the vocal folds, that reduced air pressure will allow the vocal folds to move toward each other more quickly than they might otherwise. So the idea is when there's air flowing between the vocal folds after the pressure is released, the vocal folds actually get kind of sucked together by very reduced air pressure. This takes place during the elastic recoil part of the glottal cycle. So once that subglottal pressure is released, the vocal folds can return back to their original adducted position that the muscles are trying to hold them in. This closes off the glottis. The Bernoulli effect helps bring those vocal folds back together quickly as well. So we have a cycle of opening and closing of the glottis because of the interaction between the elastic vocal fold being held adducted by muscles and the subglottal air pressure pushing that elastic vocal fold open. And then the cycle starts again. Once the glottis is closed, air pressure begins to build, and the cycle starts over. This cycle happens very rapidly, so more than 100 times per second in almost all cases. And we have a very precise balance between subglottal pressure coming from expiration and elasticity of the vocal folds due to their structure and how they're held closed by muscular tension. If we think informally about other ways we can make sound, like banging on a drum, or blowing a raspberry between your lips, or strumming a guitar string, or whistling, phonation is most like one of these. And the one it is most like in terms of how the noise is made is blowing a raspberry. If you push air between your lips, like air pressure blows the lips apart, muscular tension is trying to hold the lips closed, and so doing those two things at the same time, you end up with a cycle of lip vibration that's similar to phonation. And just for fun, there are a variety of animals that make noises. Birds sing and chirp, cats purr, crickets sing by rubbing their legs together, dolphins make a whistling noise. The one of those that actually involves a phonation-like process is bird song. Birds have a thing called a larynx that is similar to a larynx that is used for a phonation-like thing. Most people guess it's the purring of a cat, but actually cat purring is done by a cyclic muscular contraction that's kind of special to cats.